Hi everyone. So this is our year 13 live stream, and I thought what I would do, because last time I did it for like year 12 and year 13, so I thought that this time, instead of it being year 12 and year 13, what I would do is I would just do just year 13 specific. And I'm going to be looking in today's live stream at differential equations and some other really tricky implicit differentiation. So yeah, so we're going to start off with some differential equations. And let's have a look at this particular question here. So this one says, it says water flows at a constant rate into a large tank. The tank is a cuboid with all sides of negligible thickness. The base of the tank measures 8 meters by 3 meters, and the height of the tank is 5 meters. There is a tap at a point T at the bottom of the tank as shown in figure 5. At time T minutes after the tap has been opened, the depth of the water in the tank is H meters. Water is flowing into the tank at a constant rate of 0.48 meters cubed per minute, and the water is modeled as leaving the tank through the tap at a rate of 0.1 H meters cubed per minute. Show that according to the model, 1200 dH by dt is equal to 24 minus 5h. Okay, so right, that's our first thing. So the first thing I would say is notice that in the question, we've got to find an expression for dH by dt down here. So it says dH by dt. So, but the question's talking to us about the rate of change of volume. So what we've got is dV by dt, that's going to be the rate in. So if I write down here, the rate that water comes in minus the rate that the water goes out. So the rate of change is equal to the rate that the water pours in minus the rate that the water pours out. And the question tells us it's flowing in at 0.48 meter cubed per minute, and it's flowing out at a rate of 0.1 H meter cubed per minute. So that is our dV by dt, the rate of change of the water. Now, in this question, we're not looking for dV by dt, we're looking for dH by dt. So we're going to use the chain rule, and this is the way that I prefer to do it with the chain rule. I like to write down dH by dt is equal to dH over something times by something over dt. So we've got our chain rule there. And when we think about the context of this question and think about what is that missing thing going to be, it makes sense if that missing thing is dV. So we've got dV is going to be our missing component there. So now we've got the connection that we need to be able to find our dH by dt. So dH by dt is going to be dH over dV times by dV by dt. Now we know our dV by dt because we already know that that is the rate at which the water is pouring in minus the rate at which it's pouring out. So we've got dV by dt. So we just need to find a way to get dH by dV. Well, we can figure out the volume of the water in the tank because the volume is going to be 3 times 8 times by h. So therefore, we can figure out what dV by dH is, the rate of change of the volume. So the rate of change of the volume, dV by dH, we're going to differentiate the 24h with respect to h. And that just gives us 24. So dH by dV is going to be the reciprocal of dV by dH. So it's going to be 1 over 24. So therefore, we've got our expression for dV by dt is going to be our dH by dV, which is 1 over 24, times by our dV by dt. So we've got an expression now that's looking like it's going the right way, almost there. All we've got to do with this now is, if we multiply both sides by 24, we get 24 dH by dt equals 0.48 minus 0.1 h. And then if we times both sides by 50, we end up with 1200 dH by dt is equal to 24 minus 5h as required. So that's part A done. So that was quite useful, I think. Now, what's next? It says, given that when the tap was open, the depth of the water was 2 meters, show that according to the model, h is equal to that expression there. So what we've got to do now is we've got to solve this differential equation. So let's have a look and see how we're going to solve this differential equation. So here's our expression. And we're going to use a technique called separating the variables. Okay, so we're going to separate the variables. Now, what that means is you basically get everything that has a h over one side of the equation, and everything else is going to go over the other side. Okay, so we're going to have 1,200, and we're going to have 24 minus 5h is going to be on the other side of the equation. So I've divided everything essentially by 24 minus 5h. So we're going to integrate both sides. So we get the integral of 1,200 over 24 minus 5h is equal to the integral of 1 with respect to t. So when we use the chain rule backwards to integrate this, we have 1 over something goes to ln. So that's going to go to ln 24 minus 5h. But we've got to remember that when you use the chain rule backwards, you've got to remember to divide by the derivative of the inner function. And the derivative of 24 minus 5h is going to be minus 5. Okay, so when you divide by the derivative of the inner function, you're going to be dividing by minus 5. So 1,200 divided by minus 5 is minus 240. Okay, so we just use the chain rule backwards there to get our minus 240. So now we've got, this is what we would call our general solution. Okay, so GS for general solution, which is like a fancy way of saying we don't know what the constant is. But they give us a piece of information in the question that helps us to work out what the constant is. And the information they give us is they tell us that when the time is equal to 0, the depth of the water in the tank is 2. So we can, that's called a boundary condition, that initial piece of information. So we can insert that into our equation in order to help us find out what the value, find out what C is going to be. So we've got the H is 2 when the time is 0. So I've just put in there H is equal to 2 when the time is 0. So that gives us, we've got ln of 24 minus 10, which is ln 14. And then we've got 0, add C. So we found out now that our constant is minus 240 ln 14. So now bringing that together, we know what our constant is now. So we've got minus 240 ln 24 minus 5h is equal to t minus 240 ln 14. So what I'm going to do now is I'm going to take that ln 14 across to the left-hand side of the equation. And then because we've got a subtraction, it's going to turn into a quotient, okay? So because we've got a subtraction, it's going to go into 240 ln 14 minus 240 ln 24 minus 5h. So that's going to go into a division, okay, using the laws of logs. So we're getting there now. So we've got now 240 ln 14 over 24 minus 5h equals t. And we've got to try and get h, the subject of this equation. So I would suggest that our next step is we're now going to divide by 240. So ln of 14 is equal to 24 over minus 5h equals 1 over 240t. So we reverse the logs, giving us 14 equals 14 over 24 minus 5h is equal to e to the 1 over 240t. Then we're going to multiply both sides by 24 minus 5h. So we multiply both sides by the 24 minus 5h, expand the brackets. So that one times that one times that one. And we're now going to get everything that has the h over one side of the equation. Okay, so everything with the h is going to come across to the left-hand side. So we're going to put 5h e to the that is going to come over there, and the 14 is going to come across to the right. So we're now getting there. We're getting close to our solution. So the last step now is just to divide by 5 e to the t over 240. So when we do that, we get that h is equal to 24 e to the t over 240 divided by 5 e to the t over 240. And then we get 14 5 e to the t over 240 there. So here they're going to cancel like so, and just leaving us with 24 over 5. And this e to the t over 240 can be brought up to the numerator and written in the required form. It's going to be e to the minus 1 over 240 times t. And that's it. We've done it. We've got that in the required form now, okay? Because we've got h is equal to 24 over 5 minus 14 over 5 e to the minus 240t. So that is that one done, part B. Oh my goodness. Now, this next thing is such an important idea. I can't emphasize how important this next idea is. Super important idea. So for part C, it says, given that the tap remains open, determine according to the model whether the tank will ever become full, giving a reason for your answer. Now, honestly, the number of times that this comes up, it's kind of ridiculous. I think everybody who's doing A-level needs to know this point because it so comes up so often, it's almost kind of guaranteed to come up in a way. So there's a graph I've drawn of e to the minus t over 240, okay? Now, as t tends to infinity, you'll notice that this graph is tending towards 0, okay? So what that means is the long-term behavior of this particular equation is that as time gets bigger and bigger and bigger, that bit there is going to become vanishingly small. It's going to disappear. So that means that the height, h, is going to tend towards the 24 over 5. Now, 24 over 5 is equal to 4.8 meters. So basically, the long-term behavior of the fluid in the tank is that it's going to move it's going to tend towards 4.8 meters, which means that the tank will never become full. Okay, so that is that question. Really nice kind of differential equation question there. Right, let's have a look and see what we're going to do next. This one looks like a good one. A spherical mint. Okay, so this one is forming and solving a differential equation. So let's have a look at this one. So in this question, what does it say? It says a spherical mint of radius 5 millimeters is placed into the mouth and sucked. 4 minutes later, the radius of the mint is at 3 millimeters. In a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. Okay, so we can form a kind of like proportionality statement from this. We can say that dr by dt is proportional to 1 over r squared. And we can change that proportionality statement into an equation by introducing a constant of proportionality. So we can say that means that we can say that dr by dt is equal to k over r squared. Okay, so dr by dt is going to equal k over r squared. So now we're going to do the same thing that we did previously. We're going to separate the variables. Okay, and separating the variables means we're going to treat the dr by dt as though it was a fraction. It's not actually a fraction, but we're just going to treat it as though it was a fraction. So we're going to multiply both sides by r squared. So we get r squared dr, and then multiply both sides by dt. So that gives us kt. So therefore, we now have separated our variables, so we can now integrate both sides of our equation. So when we integrate it, hi there, Blue. Thank you for saying hi there. That's good. So I'm just going over some differential equation questions, okay? So if you have any questions on what I'm going through, please do let me know. So yeah, I'm going to raise the power by 1 now and divide by the new power, okay? So raise the power by 1, divide by the new power, and the k is going to go to kt at c, okay? So we've basically integrated the power by 1. Now, this is what we call our general solution, okay? That's our general solution. And we need a boundary condition in order to be able to work out what the constant is. And in fact, actually, it's worth noting in this one that we've got 2 unknowns. We've got a k is unknown and we've got c is unknown, okay? So we need to work out what those unknowns are. Now, when you've got 2 unknowns, you need to have 2 boundary conditions. And they've given us 2 boundary conditions in this question because they told us that initially the mint had a radius of 5 millimeters. So when t is 0, the radius was 5. And then they said that 4 minutes later, the radius was 3. So when t is 4, r is 3. Okay, so we're going to use those 2 pieces of information to work out k and to work out c. So first of all, let's use the information that t is 0. So when t is 0, r is equal to 5. Subbing that in, r is 5, t is 0. 5 cubed is 125. So we end up c is 125 over 3. So we put 125 over 3 there as our c. Now let's put the other boundary condition in, that the radius is 3 when t is 4. So we've now got 3 cubed. A third 3 cubed is equal to 4k plus 125 over 3 by putting in that extra boundary condition. And we're almost done now. With the only unknown in this equation is k, so we just rearrange it to make k the subject. So 3 cubed is 27, divided by 3 is 9. Take away the 125 over 3, divide it by 4, and that gives us k. So k in that case is minus 49 over 6. So we've now got our complete model, okay? So our complete model is 1/3 r cubed is equal to minus 49 over 6t plus 125 over 3, okay? And that is our particular solution. So that's our 5-mark answer to part A. So it says find an equation linking the radius of the mint to the time. So that one is done, okay? Okay, good. So you want to know, may I summarize this question and my thought process from the start of A? Yes, I can. I can go back, if you like, to the start of A just real quick. So basically, Blue, this is what I was saying, yeah? In this question, this is forming and solving a differential equation, okay? So it says a spherical mint of radius 5 millimeters is placed in the mouth and sucked. And it says that in a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. So what you do is you set up this proportionality statement. dr by dt is proportional to 1 over r squared, a bit like in year 11 when you were doing those kind of like solving things in year 11. Then you change it into an equation by introducing the constant of proportionality, k. And then depending on whether you've got this far in the integration chapter or not yet, we're going to do a technique called separating the variables, okay? And separating the variables is where you treat dr by dt as though it was a fraction. And you essentially times both sides by dt, so it ends up over there. And you times both sides by r squared, so it ends up there. And that is called separating the variables. Then you just integrate both sides. The left-hand side with respect to r, the right-hand side with respect to t. And that gives you what's called a general solution, okay? And that's just the name for a solution when you don't know what the constants are. Now, once you've done that, you need to work out, we've got two unknowns, k and c, and you need two pieces of information to work those out, okay? And the way that you work them out is by just subbing them in, and that's what hopefully I think you've been with us from then, Blue, for the rest of it. So that's how you do that to work out. From there, you work out your constants. Okay, I hope that answered your question on that bit. So that's how you start that one off. And now we've got our equation. So let's see what the next bit is, part B. Part B, it says, hence, find the total time taken for the mint to completely dissolve. Okay. Now, for this mint, yeah, good. I'm glad you understand. That's good. So for the mint to completely dissolve, when the mint's completely dissolved, it's going to have a radius of 0. So in our equation, and it's quite nice the way they do this. Oh, actually, I was going to say they give you the equation, but they don't in this particular one. So it isn't nice. You've got to get that equation. You have to get part A to do part B. So when the mint's dissolved, it's got a radius of 0. So we just put radius equal to 0, and we've got to solve for t. So we add 49 over 6 across to the other side. We're then going to times by 6 and divide by 49, and that gives us 5.102 minutes. And 5.102 minutes, that is, we can work that out. That is basically going to be 5 minutes and 0.1 minutes. So we want it in minutes and seconds. So we times that by 60, and that's 5 minutes and 6 seconds when you times the 0.102 by 60. So that's that bit done. Now there's a little modeling assumption. So it says suggest a limitation of the model. And there's so many things. They're very, very generous about what they would accept for this. One of the primary limitations of this model is that for very large values of t, you'd have a negative radius of the mint, which I think has to be the main limitation of this model. Okay, so you could end up with a negative radius for this mint, which is like clearly makes no sense. All right, I'm going to do one more differential equation question, and then after that, I'm going to do a grade, not grade 9, an A-star implicit differentiation one. Okay. So one more differential equation question. Let's have a look. Right, this one, I know from past experience, students find this question quite confusing. So this one is a little bit tricky. Oh yeah, and this one is very tricky, I think. Not a nice question in my opinion. So after this question, we'll do some, I'll do some implicit differentiation ones. So this is quite a tricky question, definitely an A-star question. And what's it saying? It says a scientist is studying a population of mice on an island. Now, the number of mice, n, in the population t months after the start of the study is modeled by that equation. N is equal to 900 divided by 3, add 7, e to the minus 0.25t. Okay, so it says find the number of mice that at the start of the study. Okay, so at the start of the study, we've got time is equal to 0. So we've got 0 in that equation there. Now, when we have 0 there, we're going to have e to the 0, which is just going to be 1. So we're going to have 900 over 3 add 7, so 900 over 10. So there were 90 mice at the start of the study. So fair enough. Now, part B, show that dn by dt, the rate of growth of the mice, is given by that equation. Now, this, in my opinion, is super tricky. So bear with me on this one because it's really not nice. So the thing we've done is, first of all, I've rewritten 900 over as 900 times something to the minus 1. Okay. Now, when we differentiate this, we're going to be using the chain rule. Okay. Now, let's think about our chain rule. We times by the power that's there, and then we lower the power by 1. So we've got minus 900, and notice the power has gone down to minus 2. But remember that with the chain rule, you've got to then times by the derivative of the inner function. And the derivative of this inner function is going to be 3 goes to 0. We've got the 7 e to the minus 0.25t. So I write that down. But then we've got to times by the derivative of the inner function, which is the minus 0.25t. So when you differentiate that, you just get minus 0.25. So when you use the chain rule to differentiate that expression, you get this really horrible thing here. Now, the difficult thing is we've got to try and prove that this is equal to this n is times by 300 minus n over 1,200. So the first thing I've done is that minus 2, I've taken that power, put it down and thought of that there as a 1. Okay, so I've kind of like used up one of those. And the reason I've done that is because 900 over that is n. So we've got an n in the equation now. So I've got rid of that and used one of them to make an n. Now, the next thing I've done is, remember that's gone now, that's been used up. I've got this 7 times by this 0.25. Okay, so 7 times by 0.25. And I've got still one of these 3 plus 7 e to the minus 0.25t's. So I've put that there, okay? And then we've still got times by e to the minus 0.25t. Now, there's a bit of a sneaky thing here. What I've done is I've engineered this into being another n. So I've basically written down a 900 in the numerator, but compensated by writing a 900 in the denominator. So I'm reverse engineering now another n by making up a 900 in the numerator and a 900 in the denominator. So that means I've got another n there now. Look, 900 over that is another n. So I've engineered another n. But I'm left with 0.25 times by 7 over 900. Okay, so that's what I'm left with. So I've just written that down there. And that, by the way, when you work it out, is 7 over 3,600. So far, so good. We've basically been able to get this down to n times by 7 over 3,600 times e to the minus 0.25t. So it's not over yet, because now we've got to rearrange our original equation to get rid of that e to the minus 0.25t. So let's have a go at doing that. So I'm now rearranging the original equation in order to make the e to the minus 0.25t the subject, so that I can then sub that in. So first step is I've just swapped over those two. So written it as 900 over n. Okay, and then, okay, that's, you can go and get some to eat and then come back. That's fine, no problem. Then I'm going to swap these over, and then we're going to basically, what we're going to do then, take 3 off both sides and divide by 7. And that gives me e to the 0.25t. So I now take logs of both sides. Oh, actually, what I've done is I've written this as a single fraction. So 900 over 7n minus 3 times 1/7. But I've multiplied the numerator and denominator by n, so we get a common denominator. So that is that whole thing over a common denominator. Okay, so that is my e to the minus 0.25t. So that gets subbed in now into my differential equation. So I've now got dn by dt is n times 7 over 3,600 times by this rearranged version of e to the minus 0.25t. Okay, we're getting close now. So basically, let's see what happens. We can take a factor of 3 out of this numerator, giving us 3 times 300 minus n, and that looks really promising. And then the 7s cancel there. One of the n's cancels there. That factor of 3 cancels with 3,600 to become 1,200. And when you boil it down by cancelling those things out, we're left with that dn by dt is equal to n times by 300 minus n over 1,200 as required. And I think that has to be the world's hardest 4 marks. I mean, it's kind of ridiculous the amount of work that you've got to do there for 4 marks. But nonetheless, that's part B. Now, this next bit is worth 4 marks and also confuses students, in my opinion. So it says the rate of growth is a maximum after t months. Find, according to the model, the value of t. Well, let's have a try and visualize what's going on here. So here I've drawn a little sketch showing this is the n, the number of mice, and this is the rate of change of mice. Okay. Now we know that on our equation, dn by dt, this is going to equal 0 when n is 0, because you're going to have 0 times something in this equation here. And it's going to equal 0 at 300, because you're going to have 300 take away 300. So we're going to have a rate of growth of the mice is going to be 0 at 0 and 0 at 300. So by symmetry, the maximum rate that the mice are going to be growing most rapidly when there's a population of 150 of them. Okay, and this bit always confuses people. So we're saying that the mice are growing most rapidly, that have the biggest value of dn by dt when there's 150 mice. And we've got to try and find out what the value of t is when this happens. So what we do now is we basically put that equal to 150, the original equation equal to 150, and solve for t. So again, I've swapped over those two in this line here. I'm then going to subtract 3 and divide by 7, take logs of both sides. So that boils down to be ln of 3 over 7, divide by minus 0.25, put that on my calculator, and that gives me 3.38 months. Okay, so therefore, which I've rounded to 3.4. So the mice are growing most rapidly after 3.4 months, but quite a tricky little bit there, I think. Right, last bit of the question, and again, it's one of those things that comes up so often, it's ridiculous. It says, according to the model, the maximum number of mice on the island is p. Find out what p is. Well, if we go back to our original differential equation, let's just have a look at it. So there's our original differential equation. Now this e to the minus something is an exponential graph that's a negative exponential. So here is e to the minus 0.25t. And notice that as t gets bigger and bigger and bigger, this graph tends to 0. So what that means is that in this equation, as t tends to infinity, that bit completely disappears. And so the equation becomes 900 over 3. So the long-term behavior of that equation is it goes to 900 over 3. And so therefore, the long-term population of the mice is going to go to 300 is our answer. Okay, hopefully everyone was okay with that. If you do have any questions when I'm going through it, just put them in the comments and I'll stop and answer your question. Right, now the next thing I want to do is, that's 3 differential equations that we've done. The next thing I want to do is, oh my goodness, this is a grade A-star question. And this is the last question on 2024 paper 2 for Edexcel. Okay, now, and it's a super tricky one. I mean, it's worth 12 marks. It's the last question, and yeah, there's some really complicated algebra going on here. So let's have a look at this one. So this is going to be an implicit, doesn't mention the word implicit, expects you to understand that we're going to have to be using implicit differentiation for this one. Okay, so it says the curve C has the equation x add y cubed is equal to 3x squared minus 3y minus 2. And we've got to find an expression for dy by dx, okay? Normally, in the textbook, when they want you to do this, they make life easier by giving you a point to sub in, but they're feeling mean on this one, so they haven't. So it's just going to be all algebraic, okay? So let's now, before we can differentiate this x add y cubed, I think it makes sense for us to expand it first, because it's just going to make our life easier if we do that. And I've used the binomial to expand this, okay? So what I've done is said is this x cubed for the first term, and then 3x squared y. And then the next term, I'm going to have 3xy squared, and then y cubed. So if you want a really kind of quick shorthand way of expanding a cubic, or indeed a quartic or anything, I've made use there of the binomial expansion. Okay, so it's just a kind of a quick hack for expanding a triple bracket. The right hand side, there it is. So let's think what's going to happen when we differentiate these various bits of this equation. Well, the x cubed, that's nice. That's just going to go to 3x squared, no problem. This bit, 3x squared y. Now, hopefully you're saying to yourself, that's going to be the product rule. And if you are saying that, you are correct. So the product rule is going to be used to differentiate this. So I've called my u 3x squared, and I've called my v y, okay? So my u dashed is going to be 6x, and my v dashed is dy by dx. Now that's implicit differentiation because you can't differentiate y with respect to x. So you write dy by dx. So my product rule is going to be u dash v and u v dashed. So my u dashed is 6x, my v is y, my u is 3x squared, and my v dashed is dy by dx. So that expression there is the derivative of 3x squared y. Okay, now we've got to differentiate 3xy squared. So we've got another lot of the product rule. So this time my u is 3x, my u dash is 3, my v is y squared. My v dashed is going to therefore be 2y dy by dx. Okay, so 2y dy by dx. So putting it into the product rule, u dash v and u v dashed is going to go to 3y squared, because my u dashed is 3 and my v is y squared. And my u v dashed is going to go to 3x times by 2y by dx there, which goes to 6xy dy by dx. So that is that term differentiated. So we've done that one, and that one. Now we've got to differentiate this one, y cubed. And y cubed is going to go to 3y squared dy by dx. So the left-hand side is all differentiated now. Right-hand side, 3x squared goes to 6x. 3y goes to minus 3 dy by dx, and the 2 disappears. Okay, so we've now got as far as this line here, and my goodness, that looks horrific, doesn't it? Looks like an accident waiting to happen in terms of like losing a sign, dropping a sign or something. So what's our strategy going to be from here? From here, we're going to gather together everything that's got a dy by dx in, and everything else is going to go, everything with a dy by dx go on one side and everything else on the other, okay? So that 3x squared, it's going over to the right-hand side. I'm going to cross it off and just show that it's gone across to the right-hand side. It's gone over there. The 6xy, it's going over to the right-hand side as well. There it is, minus 6xy. 3x squared dy by dx, it can stay there. 3y squared, it's got to go over to the right-hand side. There it is, whoops, cross it out there, and there it is, minus 3y squared. 6xy, it can stay on this side, so it's staying on this side. 3y squared dy by dx, it's staying on the left-hand side as well. And then finally, that 3 dy by dx has to come over to this side, and it's joining us there on the left-hand side. And the 6x is just staying where it is. So we've got everything with dy by dx on one side now. So we factorize out our dy by dx and divide by the bracket. So we get this horrific expression here, 6x minus 3x squared minus 3y squared minus 6xy all over 3x squared plus 6xy plus 3y squared plus 3. And as if that isn't bad enough, I mean, you could leave it there. And I think that the mark scheme says that if you leave it like that, they would give you the marks. However, if you're interested, there is further factorization that can happen. And I'm going to show it you just because, you know, you might get a question where they ask you to do this. Okay. So here we have got, I've changed the order of things, and I've taken out a minus from these three terms here. And when you do that, you get x squared plus 2xy plus y squared. And that pattern you might recognize as being x add y all squared. So the numerator rather neatly factorizes into 2x minus x add y all squared, okay? And look in the denominator here, x squared add 2xy add y squared. We've got another x add y all squared there. So that can be written as x add y all squared there as well, okay? So both in the numerator and the denominator, there was further factorization that could happen there. So they'll give you the marks for that. But, if you're being ultra purist, you could basically factorize it further and get that expression there. And it's not inconceivable that they could ask you to do that. So that's part A done for 5 marks. And that was, a lot of places where you could drop a sign or make mistakes there. Part B is quite nice, though. It says the point 1, 0 lies on C. Show that the normal to C at P has that equation there. Okay, so we need to know the gradient of the tangent. We need to know what dy by dx is at the point P. So we sub in 1 and 0 into our expression here that we've got. So that's going to give me 2 times 1 minus 1 squared over 1 squared plus 1. So that gives a dy by dx of a half. So that's my gradient of my tangent, okay? But we're after the equation of the normal, so we need to do negative the reciprocal of the tangent, giving us minus 2. So that's our minus 2 there is our gradient of our normal. We've got the point 1, 0. So now, really nicely, it's just going to be y minus y1 equals mx minus x1 using the point 1, 0. So the y is 0, the m is minus 2, and the x is 1. Okay, so therefore we get y is equal to minus 2x add 2 as required. So that was quite nice for that bit. Last bit. Now this next bit again, 5 marks. This is the last kind of 5 marks on the entire paper. So I think we can expect this to be quite tricky again. So, and in fact it is. Yeah, it is a little bit tricky, but really, really important A-star idea coming up right now. So we've got to prove that this normal that we've got does not meet the curve C again, okay? And it says you should use algebra and make your in your proof and make your reasoning clear. So what we're going to do here is I've just drawn a little sketch. Who knows what that curve looks like? I've just drawn a squiggle, okay? But we have our tangent and we've got our normal, and this is our normal that has the equation minus 2x add 2. And the idea is we've got to try and prove that this line does not intersect that curve at any point apart from P. So I've subbed in the equation of the line into the equation of the curve. In other words, the equation of the normal, y is minus 2x add 2. I've replaced that for y there, okay? So I've subbed in the equation of minus 2x add 2 into our x add y, okay? Then I've collected like terms, so x minus 2x is minus x. So we've got minus x add 2 all cubed, okay? So that is that expression there. Now what I'm doing is I'm basically just expanding that whole thing using the binomial again. So we're going to have minus x cubed is minus x cubed. We're going to have 3 times minus x squared times 2 to the 1. Then 3 times minus x to the 1 and 2 squared plus 2 cubed. So all that's happened here is I'm using the binomial to expand that, okay? And then that right-hand side, I've just expanded the bracket there. So minus 3 times minus 2 goes to plus 6, and minus 3 times plus 2 goes to minus 6. So therefore, I'm now just going to collect like terms and tidy everything up. So tidying everything up, we end up with this expression here. And then taking everything over to one side, we get to this stage. So this is our equation that's been formed by subbing in the equation of the normal into the equation of the curve. Okay, so where do we go from here? Well, this is the really tricky thing, I think. We know, don't we, that x equals 1 is a solution to this equation. And we know that because we got this equation by subbing in. We know that the point P is a point on the line of the equation that we subbed in. So therefore, x is equal to 1 is a solution to this equation. And if x equals 1 is a solution to this equation, it means that x minus 1 must be a factor. So hopefully you can see where I'm going to go with this now. I'm going to do some algebraic long division, because if x minus 1 is a factor of that equation, I'm going to divide by the x minus 1 now. Okay, so using algebraic long division, I'm going to say, I look at the x, compare it with the x cubed. I say to myself, what do I need to do to that x to change it into x cubed? The answer is times it by x squared. So I times x minus 1 by x squared, giving me x cubed minus 2x. I then subtract these two from each other. So that take away that is nothing. And minus 3 minus minus 2 goes to minus 2. Drop down the 18x and repeat the process. I look at my x, I look at my minus 2x. What do I need to do to minus 2x, to x to change it into minus 2x? Times it by minus 2. So you times it by minus 2 and take them away from each other. That gives you 16x. You compare the x with 16x. You've got to times it by 16. You times x minus 1 by 16, giving you that. And then you subtract them from each other and you get 0. So now we're at the absolute key idea here right now. So what we've got now is that the equation that we got by subbing in the equation of the normal into the curve has been factorized now into this. Now, if it's the case that the discriminant of this quadratic is less than 0, then it means there's going to be no further solutions to this equation coming from this quadratic, okay? So I'm going to evaluate the discriminant of that quadratic. So b squared minus 4ac is minus 2 squared minus 4 times 1 times 16. And when you work that out, that turns out to give you minus 60. Okay, so minus 60 is less than 0. So therefore, there are no solutions coming from this quadratic. So that means that x minus 1 gives rise to the only solution. So x equals 1 is the only solution to that particular equation, which means that the line 2x minus 2, minus 2x plus 2 rather, only meets the curve once. Okay, right. So but you say, I don't understand how it gets factorized into x squared plus 2x plus y at the start. How it gets factorized to that. Yeah, so I think you're referring to, let me just have a look here. I'm just going to go back to the stage that I think you're asking about, right? I think you're asking, if I'm not mistaken, about this bit here, the x squared 2x. Is that the bit you're asking about how that gets factorized? Yeah. If you're saying you don't understand where that gets factorized from, the answer to that question is just recognizing that x add y all squared expands to x squared add 2xy add y squared. So it's just basically from memory. So just recognizing that that factorizes into that from memory. Okay, so the answer to your question is how we go from here to here is take out a minus, which leaves you with that. And then it's just pattern recognition. It's just recognizing from memory that that factorizes into x add y squared. Okay, so that's how you do it. And then likewise here, the same thing in the denominator, that just factorizes into x add y squared. Okay, so that's how I knew that that bit and that bit gets factorized into those. It's just literally just by memory. I hope that answers your question there. Perfect. All right. Well, that I think I'm going to call it a day on that live stream. I just want to say that I'm doing like a free trial. If anybody wants to join, have a little taster session in one of my groups. I've got 2 year 13 groups, and they're both going great guns. We're looking at integration at the moment. So if anybody wants to have like a free trial in one of my groups, I'm going to put a link in the description for this live stream. So when the live stream's processed, I'll put a link, and you can click on that link and put your details in there, and I'll send you some instruction. I'll send you a Zoom link so you could join us and have a free taster session, because I think you might find it really, really helpful to actually see what it's like in my groups, yeah, and have a little free taster session. So if anybody's interested in joining us, I'm going to put a link in the description of the live stream, and you just need to click on that link, enter your details, and I'll send you the details through about how you could join us in one of our year 13 classes. So they take place on a Monday and a Thursday, and it would be great to have you guys there. But I hope you found that helpful, and I'll look forward to seeing you again in the next video. All right, thanks everyone. See you later. Bye. Got to work out how to end. Oh yes, let's click on here. That's it.